Hello, good day. Today we are going to discuss this homogeneous function in our subject, a differential equation, and this is due to the request of some of our colleagues, no, from this study group. And proceeding, no, with our topic today, we have here these simple definitions for this homogeneous functions, differential equation. So we take first these polynomials where all terms are of the same degree. And by definition, polynomials in which all terms are of the same degree are called homogeneous polynomials. Okay? So if one term has a different degree from the other term, so we can say that it is not a homogeneous polynomial. Okay? So from our examples, actually we have three, no? So we will discuss first this x squared minus 2xy plus 4y squared, no, as our first example. So based on this one, we actually have three terms, no? This first term, the x squared, the second term is this 3xy, and the third term is this 4y squared. So based on this one, we will scrutinize, no, and examine the first term, the second term, and the third term. Okay, so from this, this would be, so in our first term, its exponent is 2, so we can say that the degree here is 2. Okay, for our second term, for the x is we have 1, and for our y is 1. So if you sum up this one, so 1 plus 1 is 2, so the degree, no, of our second term is 2 also. And for the third term, we have y, no, raised to the squared, so our degree is 2. So we can say that this is a homogeneous polynomials of degree. What is the degree? Second degree. Okay, so this is a homogeneous polynomials in or of the second degree. Okay, so how about this second example here? First term is x cubed, so we have here 3, no, and the second term is cube, no, y to the cube, so we can say that this is a third degree, no, homogeneous polynomial. Okay, and for our last example here, the first term is x to the fourth y, so we have here 4 for the x, and for the y is 1, so if you sum up this one is 5. Okay, and for the second term is 5, no, so we can say that this is a homogeneous polynomial again, and this is of the fifth degree. Okay, this is of the fifth degree. So we are done, no, with these homogeneous polynomials in terms of its degree, no, if it is first degree, second, third, and so on and so forth. Okay, so proceeding now to our next slide, so we will discuss, no, the concept of homogeneity, in which when a certain variables are thought of as lengths, no, a function has the physical dimension length to the kth power, then we shall call that function as homogeneous of degree k in those variables. Okay, so we have here, no, example problem for this one, no, for this concept of homogeneity. So if we take this, no, as our first example, we have a certain function, no, a function of your x and y, which is equal now to 2y raised to the cube, okay, times e raised now to the exponent of y over x, okay, minus this quantity here, we have x to the fourth, okay, and the denominator is x plus this 3y. Okay, so first, no, homogeneous of degree k in those variables. So again, we will examine each term. So for our first term here, this is, if we took the degree, about the degree of this first term, so probably we have this variable y raised to the cube, so we can say that this is third degree, third degree. How about this second term? So actually this x, to the fourth over this x plus 3y is just simply equal now to the x to the fourth times this. We raise this one up, so x plus 3y, and its exponent is raised to the negative 1, so if we raise this one up, so its exponent is just simply the negative, the negative of your 1. So we have here x, for our x to the fourth, for the first x we have 4, okay, and here for our next x we have negative 1, okay, because of this exponent of negative 1. So if you are going to sum up that one, 4 plus negative 1 is just simply equal to 3. So this 3 is just also equal now to the degree of the first term. So we can say that this is a third degree also. So we can say that this function is homogeneous, we can say that function is homogeneous, and we may type it here, function. So the function is homogeneous, okay, of degree. So we have here degree 3, in x and your y, okay. So this would be it, for this one. The function is homogeneous, for, so we have to maybe this arrow here. So again, so we will put here. Okay, so excuse me now regarding this one. So we will put here the function is homogeneous, okay. The function is homogeneous of, so degree 3, okay, and x and our y variables, okay. So that is for our first example, and we have this another example, for our second example we have here how about this square root of your x plus 4y, okay. So we can write this one into this form, x plus 4y raised now to the 1/2, okay. So again, with the concept of homogeneity, we can say that this is homogeneous. The said function is homogeneous of degree 1/2, okay. So we have here of degree 1/2. Okay, so it is a homogeneous of degree here. So we put text here 1/2, 1/2 in variable x and your variable y, okay. So this is it, for this concept of homogeneity, in which we are going to determine if the said function is homogeneous, or if it is homogeneous, so we determine of what degree is the said function. Okay, so this is now for this concept of homogeneity, and we will proceed now to our next slide, no, which is the equations with homogeneous coefficients. So from here, I will give you, no, I will give you this basic equation for this topic, and we have here, if we let, no, our equation be this one, m as a function of your x and y dx plus n as a function of your x and y dy, okay, is equal now to 0. Okay, so this would be now our function, no, for this topic regarding equations with homogeneous coefficients. And after this one, we are going to have this following assumption, no, for this given equation for this m as a function of your x and y dx plus n as a function of your x and y dy is equal to 0. So if we are going to assume that if your, okay, so if you're going to assume, no, that if your m, okay, as a function of your rx and ry, okay, is equal now to this r raised now to the n rather, raised now to the n times the function of your m, no, as a function of xy, okay. And then we have here, no, take note, m as a function of your rx and your ry is equal now this r raised now to the n times the function of your m as a function of your x and y. So we actually have here, originally it is m as a function of your x and y, no, but we made an assumption here. That is why we introduced this new variable r, no, so that we can use this one here on the right side of this formula. It is in terms, no, of n times the function m, no, as a function also of your x and y. Okay, so that is the relationship, no, of this variable r here. Why is it that we have this m as a function of your rx and your ry? Because this is used, no, for the two cases here presented, r as a function of n times this m as a function of your x and y. Okay, so for our second one is n again as a function of same, no, rx and your ry is equal now to, again, no, so it is r. So okay, so it is equal to the function of your r raised now to the m, okay, times the n as a function of your x and your variable y. Okay, so take note of this one because we will use this, no, and you can even opt to use this, no, in our sample problem. And if ever that your n, no, is just equal to m, so we have here if ever that your n is equal now to m, then the said differential equation, no, we will denote this one by this de, is homogeneous. Okay, C is homogeneous. Okay, the de is homogeneous of degree n. Okay, so that would be it, no, if your n, this n is just equal now to m, so we can say that the differential equation is homogeneous of degree n, and we can say also that our r here is just a variable or a constant. It is a variable or a constant, no? So do not be confused, no, with this r, because it could be a constant or a variable. Okay, so this is no the basic no for this equation with homogeneous coefficient, and we are going to proceed now to the solution, no, of solution methods, no, of solving a given problem. So you can opt no to use the first method, the second method, or you may opt also to use the third method, no. So I will present to you, no, the solution methods by substitution. Okay, so first is we are going to for our first method, so we have here your you let no you let this one y is equal now to bx. So that is now your basic equation for this one. And after letting y is equal now to bx, so you're going to okay, y is equal to bx, and then you're going to take the derivative no of this given function or equation y equals to bx. Okay, so taking the derivative, so derivative of your y is equal now to b times the derivative of your x. Okay, b times the derivative of your x plus your x times the derivative of your x times the derivative of your v. Okay, or simply say we can simplify this one, dy, meaning derivative of your y equals to b derivative of your x plus x derivative of your b. Okay, so try to remember this one, no, because we will use this one in your calculation. Okay, so this is for the first method, no, and for the second one is we let your x is equal now to by. Okay, so just the reverse now. If in our first method y is equal to bx, so our next method is you have to use x, no, so x is equal now to b times y. Okay, so this is now our second method, and we take now the derivative of this dx is equal to b times dy, b times dy plus this y times db. Okay, y times db, and take note of this one because we can also use this no in our future calculation, no. Okay, so among the two methods here, so in our first method the y is eliminated, no, in our calculation because your variable b is introduced into the differential equation, and in the final analysis the dA takes form, no, in which the variables are separable, and then this one also after the solution the variable y, this y here is substituted back to the equation. So the same also for our second method, no, this this x, no, variable x is eliminated, no, because we introduce again this b in our differential equation, and afterwards after the solution the variable x is substituted back to the equation, no, after the solution. And for our third method we have here the assumption, no, for this third method, which is our suggested. Okay, this is now our suggested solution. Okay, so you may opt not to use this first or the second, no? If m is simpler. Okay, is m is simpler than n rather. So you're going to use x is equal now to by. Okay, again, if m is simpler than n, you use this x, no? This x equal now to by. But if your n, no? If n is simpler, okay? So we have here n, no? If n is simpler than m, so you're going to use this y is equal now to bx. Okay, so this is now our third method, no, in which we consider this one as our suggested solution. So you may opt to use one or two depending on the condition, if m is simpler than your n or your n is simpler than your m. For the first case, if m, no, is simpler than n, so you use this second, no, x is equal to by. But if your n is simpler than your m, you may opt to use this first, no, y equals now to bx. Okay, try to remember this one, no, because in our next slide we are going to proceed, no, with this simple problem, no, application regarding this topic today. Okay, so proceeding. So sample problem for today is determine the solution of the function, no, given this x cubed plus y cubed quantity dx minus this 3xy squared dy is equal to 0, and you are going to determine the solution of the function. Okay, so for our solution for this problem, so we have here the basic equation, no, for this homogeneous function. So again, no, I'll reiterate that we have this general equation m as a function of your x and y dx plus your n as a function of your x and y dy is simply equal now to 0. Okay, so do not forget this, no, you will always base your solution to this general equation for this matter. But in this case, we have this one, no? So we may write here, we have x cubed plus y cubed, okay, quantity dx plus your, okay, it's minus, no? So sorry, this is minus, no? We have x cubed plus y cubed dx minus this minus 3x times y squared dy is equal now to 0. So based on this one, our m is as a function of your xy dx. So probably our m is just equal now to this x cubed plus y cubed. Okay, and your n is just simply also equal to this. Okay, this is our general equation is positive, no? This is positive, but here in the given equation it is negative, so we can say that our n is negative 3x y squared. Okay, So next is you're going to determine, no, which is more simpler, no, your M or your N. So in our first one, the M, we have two terms, okay? We have two terms, while for our N, we only have one term, okay? So we may say that this is the simpler, okay? And we may opt now to use this, no, because this is only one term and it is simpler, so we will opt to use this one, no. N is simpler than your M. So according now to our solution methods, so if your N, no, if your N is simpler, okay, if your N is simpler than M, so we are going to use the substitution method of Y, no. Y is equal now to B times X, okay. So this would be it, no, for this one, okay. And according to this one, if you take the derivative, so your dy, derivative of your y, equals to b, derivative of your x, plus x, derivative of your b. And you're going to use this, no? You're going to use this one in our calculation later, okay? So from the given equation, no? So again, we will write here x cubed plus y cubed quantity dx, okay, so this is minus, no, dx, this is minus 3x y squared dy is equal to 0. So what you're going to do is you substitute, no, the value of your y, which is bx here, and your dy also, you substitute the value of your dy here, okay. So we have here x cubed plus, we substitute this y with this equal now to bx, so this would be bx, no, this is bx, again raised now to, this is bx, so y cube, so this is to the cube, okay. So we enclose this one with the bracket, okay. So dx minus 3x, okay, 3x, and we also have now this y here, so your y raised to the square, so again this would be bx, no, bx to the squared times your dy, which is this one, okay. So we have here, we will just quantify this one, no, b dx plus your x db, which is equal to 0. And you may opt, no, since this is one term, so you may opt also to put a bracket here, okay, bracket, okay. So after this one, we have here, we simplify this one, so x cubed plus b cubed, and then we have x cubed, okay. So this is bracket, no, dx minus, so we have here this one is b squared x squared, so this would be 3x, and then we have b squared x squared, okay, times this b dx plus your x db, quantity and bracket equal to 0. Okay, so again, we will distribute this one, no, this dx to this one, so x cubed times dx and this quantity times dx, so this would be x cubed dx plus this one b cubed x cubed dx, okay, minus, so we will have to distribute this one, no, this one to this term here, distributive law, so this would be 3x times this b squared x squared, so this would be 3, no, so 3x cubed b squared, okay, 3x cubed b squared, okay, so maybe I will just have to simplify first this one, no, so 3x cubed, okay, x cubed b squared times this b dx plus x db bracket equal to 0. Okay, so proceeding. So we will proceed, no, with our calculation. So this would be again, so x cubed dx, and then we have this plus b cubed x cubed, b cubed x cubed dx, okay, minus, so we distribute this one, no, so 3 we have this 3b cubed, no, so we have here 3 b cubed x cubed, b cubed x cubed dx, okay, and then 3 and then plus, no, so we have here plus, so 3 b squared, okay, 3 b squared times this x, no, x to the fourth, then this is db bracket is equal to 0. Okay, so we distribute this one here, okay, so we have here x cubed dx plus b cubed x cubed dx minus, no, distribute the negative, no, minus 3 b cubed x cubed dx, again minus, no, minus, so negative times positive is negative, so this is 3 b squared x to the fourth db, okay, so this is equal to 0. So this is b, no, okay, so if we are going to simplify this one, so we have here, no, first we have x cubed dx, x cubed dx, no, and then we have like terms here, no, we have b cubed x cubed and we have b cubed x cubed, no, so plus 1 and negative 3, so this would be minus 2, no, so minus 2 b cubed, and then we have here x cubed, okay, b cubed x cubed and then dx, okay, and then we have here minus 3 b squared x to the fourth, minus 3 b squared and then x to the fourth db is equal to 0. Okay, so we are going to extract, no, some common terms here, no, with dx, so we have x cubed, so we may opt, no, to extract, no, this x cubed dx, no, from these two terms here. So actually first, no, we are having this x cubed dx extracted, no, from these two terms. So this would be 1, since x cubed dx times 1 is just this x cubed dx, minus this x cubed dx na being extracted, so 2. The only remain variables are the 2b cubed, no? 2b cubed, okay? And then we have here, maybe we can extract, no? Variable x to the cube, since we have here x to the fourth, so we can extract, no, this variable x cubed from this one. So probably this would be 3. We have here 3, and then we have b squared, no, times your x, okay, db, which is equal now to 0. Okay, so after extracting this one, no, so we extract this x cubed, no. So we may rewrite this one in this form actually, no, x cubed times this 1 minus 2 b cubed, and this is dx, minus this x cubed times this quantity 3 b squared x, and this is db, no, is equal now to 0. So this x cube is eliminated, no, because if we are going to extract, no, this x cube from these two terms, and then it's just eliminate, no, because this is equal to 0. Okay, so this x cube is now being extracted again, and it will be eliminated, no, because if we are going to extract this one again, so let us just extract this one, no, before we eliminate this x cube, no. So we have here x cube times this one here, we extract, no, from 1 minus 2 b cubed, and this is dx, okay, minus we extract the x cubed, so remain is this 3 b squared x, no, 3 b squared x, and this is db, bracket, is equal to 0. Okay, so this is just being eliminated, no, after this one, after the extraction, and then proceeding with our computation. So again, we will clear this one out here on the right side. So after that one, we only have this 1 minus 2b cubed, no, times this is quantity dx, okay, minus this 3, okay, so 3x b squared, no, and db equal now to 0. So after this one, we are going to have this term, no, we transpose this second term to the right side, so we have 1 minus 2 b cubed times this dx equal now to 3x b squared db, okay. So combining, no, those terms having the same variable, so we cross multiply, no, and we combine those with the same variables. So in terms of x, so this would become here dx over this x, no, is equal also to we already get now this x, no, here, so this would be 3x, no, no, 3b squared, 3b squared, 3b squared, no, since this is already here, so 3b squared db, so db over this 1 minus 2b squared, 1 minus 2b squared. Okay, or simply this is just equivalent to dx over x is equal now to 3b squared over 1 minus 2b squared, no, db. Okay, so after this one we are going to integrate, no, so we are going to integrate this one, no, integrating. Okay, so first we are going into this dx over x, no, and later, no, we will go also to this to the integration of this term here. Okay, so we have here this integral of dx over x is equal now to the integral of your quantity here. Okay, is 3b squared over this 1 minus 2b squared, okay, dp. So we are going to get the integral of this dx over x, and separately the integral of this quantity 3b squared over the quantity 1 minus 2b squared. Okay, so proceeding. So for the integral, no, for the integral of this dx over x, so we can say that the integral, no, of your dx over x is just equal now to the natural logarithm of this variable x plus a constant c. So you have to remember, no, your integral calculus, and for this one, so we have also for integral of this 3b squared over 1 minus 2b squared db. So you may assign, no, so let us assign, no, on this one, we let, no, u is equal now to this 1 minus 2b squared, and then taking the derivative now of your u, which is equal now to derivative of 1 is 0, and then the derivative of this one is negative, no, so 2 times 2, and then b raised to the 2 minus. Okay, okay, so I'm sorry, no, this is okay, no, so let's have a correction, no, because based on this one, 1 minus 2b cubed quantity dx is equal now to this 3, no, this 3b squared db, so probably dx over x, and then there is 3b squared over 1 minus 2b cubed. So let us correct this one, no, before we proceed. So let us correct this one. This is cube, and also this one, this is cube. Okay, and this is also cube. Okay, so from here, our integral for this one is, this is to the cube. Okay, and 1 minus 2b, and this is also cube. Okay, so again, so this would be the derivative of our u is Okay, so we have here the derivative of our uh, dx over x is equal to, from your integral is ln of this x plus the constant c. Okay, so we will assign this c as our c1 here. Okay, and second is for the integral of our 3b squared. Okay, 3b squared over this quantity 1 minus 2b cubed. Okay, so db. So from here, we will assign u is equal now to this 1 minus 2b cubed. Okay, and then we take now the derivative of this u, in which the derivative of 1 is 0, and then this one is negative 2 times this one 3, and then b, and then this is 3 minus 1, and then the derivative of your b, in which our du is just simply equal now to negative 6b squared db. Okay, so after this, we are going to work with this one. So this integral of your 3b squared over this 1 minus 2b cubed db is just equal now to this one 3b squared, and then we assign our u equal now to 1 minus 2b cubed, so this is now our u, and our db, this is db, so db from here, so we can say that our db based on this one is just equal now to du over negative 6b squared. Okay, so we will replace now our db here. Okay, so this is du over negative 6b squared. Okay, so after this one, we can eliminate the b squared here, and we can simplify this one, this one. So proceeding with this calculation, we have here integral of the only thing remain here is this one by 3 is 1, so by 3 is 2. Okay, so this could be only du. Okay, du over u times negative 2, so negative 2u. Okay, so this would be for this term here, and then maybe this one we will extract this constant here, in which this would be equal now to negative 1/2 integral of your du over u. Okay, so after this one, this would be equal then to negative 1/2 times the quantity, the integral of du over u is just our ln of this u plus constant, so we will assign c2 here, because we already have this u1 here. Okay, so simplifying, this is equal now to negative 1/2, and then we substitute the value of our u, which is 1 minus 2b cubed, so this is 1 minus 2b cubed, and then we have here plus c2. Okay, and then after this one this is just equal now to, we substitute, distribute this negative 1/2 to each term, so this is minus 1 over 2 ln of this quantity 1 minus 2b cubed, and then we have here, since this is negative, negative times this c2, so this is minus 1/2 c2. Okay, So proceeding. Okay, so proceeding now with this calculation. So we have this value here. So from this one, the integral of dx over x is equal now to the integral of your 3b squared. 3b squared over 1 minus 2b cubed. Okay, and this is db. So we can actually substitute the value of our integral of dx over x and this integral of 3b squared over 1 minus 2b cubed db, in which this is equal now to ln of your x plus c1, okay, which is equal now to this one, negative 1 half. Negative 1 half of your ln of this 1 minus 2b cubed, and then minus 1 half of your c2. Okay, so after that one, we are going to transpose this constant c1 to the other side. So we have here ln of your x equal now to negative 1 half ln of your 1 minus 2b cubed, and then minus 1 half c2, and this would be minus 1 half minus c1, minus c1. Okay, so let us assign our c3 equal now to minus 1 half c2 minus c1. So these terms here, let us assign this minus 1 half c2 minus c1 equal now to c3, and then we will have now this calculation. ln of your x is equal now to 1 half ln of your 1 minus 2b cubed, okay, and then we have now this plus c3. Okay, or if we are going to transpose this one, okay, so this is actually negative 1 half, since this is negative. Okay, so we will transpose this one to the left side to get a simplified equation for this. Okay, so we have here ln of your x plus 1 half ln of the quantity 1 minus 2b cubed is equal to this constant c3. Okay, so we are going to multiply this by 2 to eliminate the fraction. So this would be equal now to 2 ln of your x plus 2 times 1 half is 1. So this would be equal now to ln of 1 minus 2b cubed is equal now to 2 times c3. Again, so let us assign let us assign c4 equal now to 2c3. So we will have now this 2 ln of your x plus ln of your 1 minus 2b cubed is equal now to c4. Okay, so after this one, we can express this one in this form. We can actually express this one, this 2 ln x is just equal now to ln x squared. So this is a property of the natural logarithm also. So this is also equal now to ln of your x squared, okay? Plus this term here, no? ln of 1 minus 2b cubed is equal now to C4. And after this one, since we have another property of the natural logarithm, no, that says your ln xy is just equal now to ln x plus ln y. Okay, so try to remember this property of the natural logarithm, in which we will apply it here also. Okay, so this is probably then equal now to ln of this quantity here, no, x squared, and then we have now this 1 minus 2b cubed, okay, is equal now to C4. Okay, so proceeding, we will have then now this a calculation here, no, from this one. Actually we can really exponentiate this one, no, exponentiating. Okay, so exponentiating, so we can have this e of this ln, no, e of that ln. So we have here ln of the quantity x squared, and then times this quantity 1 minus 2b cubed, and then this is bracket, no, and then this is equal now to e exponentiating C4. Okay, and then we have also the property, no, that of the exponent, when exponentiating, no, the ln x is just equal now to x, no. We have this property, no. I hope you can still remember this one. So from here, e to the ln of this one, so our x is referring now to this x squared times 1 minus 2b cubed. So by property of this one, so it is just equal now to the x. So therefore we can say that this one is equivalent to x squared times 1 minus 2b cubed. Okay, and this is equal now to e raised to the constant C4. Okay, and then let us assume, no, let since we already have C4, so let C5 is equal now to e raised now to the C4. Okay, so we can say that this is equivalent to x squared times 1 minus 2b cubed equal now to C5. Okay, but since we have this one, no, since we have y is equal now to b times x, so we can say that our b is just simply equal now to y over x. Okay, so we can actually substitute b here, no, in terms of your y and x. Okay, so we can have this value of, or we have an equation, no, in terms of your x and y. And proceeding with this one, okay, so we substitute, no, this one to this one, we substitute, so it is just equal now to x squared times the quantity 1 minus 2. Okay, so we will put here a bracket, no, 1 minus 2b cubed, so our b cubed is this y over x cubed. is equal now to C5. Okay, and then after simplifying this one, so we have here equal this x squared times the quantity 1 minus this is 2, no, we distribute this one, so 2 times, so this is y cube over x cube. Okay, equal now to C5. And then we also have here, we distribute these two, so x squared, and then we have 1 minus 2 y cube over this x cube equal now to C5. Okay, so again we distribute this x squared, no, so this would be x squared, then x squared times 1, x squared times this one, so this is minus, we have here 2y cube. Okay, so this one is 2 and 3, so this would be 2y cube over x is equal now to C5. Okay, so after this one, to eliminate the fraction, so we will multiply x, no, to eliminate this fraction, so distribute x times x squared, so we have here x cube minus, this one is cancelled out, minus 2y cube is equal now to C5 times x, so this is C5 times x. Okay, or we can simply say that no, that this is just equal to so let us assign, no, let C is equal now to C5, okay, as our final constant. So from here, x cube minus 2y cube is equal now to, this C5 is already C, so C times x. Okay, so we have here x cube minus 2y cube is equal now to cx, and this is probably now our final answer, no, for this problem. Okay, so this is how, no, to get, no, the solution of a given function, where in this case this is just equal to this x cube minus 2y cube is equal now to cx. And try to review, no, your calculus, especially the properties of the logarithm and even the natural logarithms, and many other properties, no, especially for exponentiating. And that would be it, no, for this day. And before we end, no, our lecture, so I would like everyone to please, no, subscribe to my YouTube channel, and if you support my YouTube channel, you can also share, no, and like. And then for our next topic, we will proceed, no, with these separable equations, or what we call the variable separable. And these are my references, no, for this lecture regarding the subject differential equations. And once again, thank you very much everyone for listening and watching. Keep safe and God bless us all.